The next section examines why creating a perfect flat map of the US is fundamentally impossible due to the mathematical challenges of projecting a sphere. The impossible perfect map. Creating a perfectly accurate flat map of the United States is impossible because of fundamental mathematical limitations. The Earth is a three-dimensional sphere, while maps are two-dimensional surfaces. Imagine trying to flatten a basketball without stretching or tearing its surface. Some distortion is inevitable. Cartographers must choose which geographic properties to preserve, always sacrificing others in the process. The Mercator projection illustrates these trade-offs clearly. While it preserves angles perfectly for navigation, it drastically exaggerates sizes near the poles. Alaska appears 2.5 times larger than its true proportion relative to the lower 48 states. If you've ever wondered why flight times don't match map distances, Seattle to Anchorage takes about as long as Chicago to Los Angeles, this projection explains the discrepancy. Your mental map of distances is likely skewed by these distortions. Equal area projections like Gall-Peters fix the size problem but create new issues. The United States appears squashed, with Florida stretching oddly wide and Alaska looking stubby. While Africa shows its true massive scale, the unfamiliar shapes make geographic features hard to recognize. This reveals a core challenge. No projection can simultaneously keep shapes, sizes, distances, and directions perfectly accurate. Compromise projections like Robinson attempt balance. The US maintains its familiar outline but appears about 15% smaller relative to the world than on Mercator. Alaska shrinks to more accurate proportions while remaining recognizable. These solutions spread distortions more evenly rather than eliminating them, like smoothing wrinkles across a sheet rather than removing them completely. The distortions become particularly noticeable when examining flight paths. On a Mercator map, a straight line from Chicago to Beijing appears efficient, but the actual shortest route curves far north over Alaska. Similarly, New York to Johannesburg doesn't fly east across Africa as flat maps suggest, but curves southward over Brazil. Your perception of these routes is shaped by projection choices you've likely never considered. Digital mapping hasn't solved these problems. While we can now view 3D globes, most apps default to Web Mercator for its computational advantages. This means we're constantly viewing size distortions without realizing it. Alaska still appears enormous on your weather app, and Africa still looks smaller than it truly is. The convenience comes at the cost of geographic accuracy most users never notice. These limitations have real-world consequences. Shipping companies adjust routes for projection errors. Emergency responders use local projections that minimize distortions in their operating area. Even GPS coordinates must be translated into whatever projection a particular map uses, introducing potential errors at each conversion. The mathematical compromises affect everything from airline navigation to disaster response. Multiple government agencies maintain different official projections for their specific needs. The U.S. Geological Survey uses ALBAs for national maps, while the FAA requires different projections for aeronautical charts. This patchwork system exists because no single projection can serve all purposes equally. Each application demands different trade-offs between shape, size, and distance accuracy. Every projection decision carries implications. Accurately representing area for resource management might sacrifice shape accuracy needed for navigation. Preserving angles for surveying might distort sizes important for environmental studies. The mathematics of map-making forces these choices with no perfect solution, only various imperfect compromises that shape how we see our world. These inherent limitations lead professionals to develop specialized techniques that adjust for inevitable distortions. Methods we'll explore next as we examine how experts work around these fundamental constraints in their mapping workflows. Cartographers and surveyors face the reality that all maps contain distortions, yet their work demands accuracy within these limitations. They employ specialized techniques to minimize errors caused by projecting the Earth's curved surface onto flat maps. Ground control points, GCPs, physical markers placed at known coordinates, form the foundation of this precision. A survey team might position 10 to 20 GCPs across a square mile, each located using high-precision GPS equipment accurate to within centimeters. Drones capturing aerial imagery then reference these points to align photos with real-world positions, compensating for distortion created by both the camera lens and map projection. Modern mapping software processes this data through multiple correction layers. First addressing lens distortion, straightening curved lines from wide-angle cameras, then adjusting for terrain elevation changes, and finally applying projection algorithms to position everything within a chosen coordinate system. This approach allows an aerial survey of Chicago to maintain centimeter-level accuracy across hundreds of acres, despite flat maps' inherent limitations. Projection selection remains critical. The Universal Transverse Mercator (UTM) system divides the world into 60 narrow zones to keep scale distortion below 1 part in 1,000, acceptable for engineering. Surveyors working on a Texas highway project might use UTM Zone 14, 102 degrees west to 96 degrees west longitude. Wider projects spanning multiple zones require custom solutions. For national scale mapping, organizations use projections like Alber's Equal Area Conic, which preserves area accuracy across all 50 states using two standard parallels, 29.5 degrees north and 45.5 degrees north. This system allows USGS topo maps to maintain consistent accuracy, whether showing Kansas farmland or Rocky Mountain regions. Ground surveys still verify digital maps. In downtown Manhattan, surveyors establish control points on building corners to account for urban canyons disrupting GPS signals. These measurements validate aerial data before finalizing products. Elevation data presents particular challenges. LiDAR surveys must account for Earth's curvature. A Mississippi River Basin survey uses geoid models to convert raw measurements into meaningful heights above sea level, adjusting for gravity variations that make sea level differ by hundreds of feet across the continent. Coordinate systems add complexity. Most U.S. mapping uses an ED83, but older surveys might use an ED27, creating coordinate differences of hundreds of feet. Professionals must apply mathematical adjustments when combining datasets from different eras. Construction projects demand rigorous distortion management. When building Michigan's Gerald R. Ford International Airport Terminal, surveyors established a custom coordinate system, positioning structural columns within 1/8 inch of specifications across the 800,000 square foot site. Emerging technologies offer new solutions. Mobile mapping systems on vehicles combine laser scanners and cameras to collect millions of 3D points per second, automatically applying corrections while driving. Chicago used this to inventory signs and pavement markings across 4,000 miles of streets. Satellite-based augmentation like the FAA's WAS system improves GPS accuracy from 15 meters to under 1 meter nationwide, allowing survey-grade precision without ground markers for applications like agricultural field mapping. Professional networks form mapping's backbone. The National Geodetic Survey's 2,000 plus permanent GPS stations track positional changes as small as 1 millimeter per year, detecting continental drift. Surveyors tie projects into this network for consistency across state lines or decades. Urban canyons present unique challenges. New York City developed a hybrid coordinate system combining state plane projections with localized adjustments, using optical instruments where GPS fails between skyscrapers. Historic projects reveal evolving standards. When restoring Washington, D.C.'s Jefferson Memorial, surveyors discovered its axis aligns 5 degrees off true north, a deliberate 1939 design choice only revealed through modern laser scanning. These techniques demonstrate how experts work within projection limitations. By combining precise measurements, advanced software and appropriate projections, they create products accurate enough for engineering and scientific purposes. The next section examines why understanding these distortions matters beyond professional circles. Why understanding distortions matters. Map distortions influence real-world decisions with significant consequences across multiple sectors. Let's examine these impacts through key categories: travel and logistics. Standard maps misrepresent flight paths and shipping routes. The straight lines on Mercator maps don't reflect actual curved Great Circle distances, the shortest paths between points on a globe. A Los Angeles to London route appears shorter than reality, affecting scheduling and fuel calculations. Shipping companies lose millions annually when routes between Shanghai and San Francisco don't account for the northern curve near Alaska. Policy and global priorities. The exaggerated size of northern nations on Mercator projections creates visual bias in international relations. When Africa appears smaller than Greenland, its environmental and economic importance gets visually diminished. During the 1982 UN Convention on the Law of the Sea, delegates had to establish special mapping standards to resolve maritime boundary disputes caused by different projections. Emergency response. During Hurricane Katrina, some relief teams wasted critical hours because Mercator maps made affected towns appear equally distant from aid centers when they weren't. First responders relying on these maps reached survivors hours later than necessary, a delay that proved fatal for some. Floodplain maps using improper projections have similarly misidentified evacuation zones during recent floods. Agriculture and infrastructure. Projection errors cause up to 15% discrepancy in reported farmland sizes nationwide, equivalent to misjudging a 100-acre farm as 85 acres. These inaccuracies affect irrigation planning and equipment needs. Pipeline routes plotted on flat maps often require extra materials when built, as a proposed 100-mile route might actually measure 110 miles accounting for terrain. Military and high-stakes decisions. In the 1991 Gulf War, artillery units reported targeting difficulties because their maps didn't adjust for projection variations across the battlefield. One unit fired shells nearly 500 meters off target, the length of 5 football fields, before switching to GPS-corrected coordinates. Modern military systems now automatically convert between coordinate systems to prevent such errors. Education and perception. Students learning from Mercator maps absorb distorted views. Brazil appears smaller than Alaska despite being nearly 5 times larger. These early impressions persist into adulthood, affecting business decisions and cultural attitudes. When New York City students were shown accurate comparisons, 68% couldn't correctly identify which of 2 trading partners actually had the larger economy. Climate science. The common 8 to 12% distortion in Arctic areas affects ice loss calculations, potentially underestimating sea level rise by inches over decades. During the 2015 Paris Agreement negotiations, some delegates initially questioned climate models until shown corrected projections of melting patterns. Urban planning. The New York MTA found subway routes required 5% length adjustments when accounting for projection effects, adding millions in costs. A proposed mile-long road might actually measure 1.2 miles when accounting for elevation changes, creating budget overruns across large projects. Public health. Early COVID-19 tracking using standard maps obscured transmission patterns between cities. When the CDC switched to customized projections, they discovered infected travelers were moving along highway corridors that flat maps had visually separated. These examples reveal how map distortions compound into real-world consequences. The container shipping industry's annual $47 million loss from routing errors could fund 1,000 new school buses. The 15% farmland measurement discrepancy equals misallocating enough water for 200,000 households annually. One striking case occurred during the 2004 Indian Ocean tsunami, when relief maps made some coastal villages appear equidistant from supply centers. Rescuers following these maps took 3 extra hours to reach one community, time that might have saved dozens given the 90-minute window for effective flood response. Later analysis showed proper projections would have revealed a direct overland route obscured by the map's distortion. Understanding these limitations helps us use maps more effectively. Tools like the truesize.com allow quick comparisons. Dragging Canada over Africa reveals the continent could contain 3 entire Canadas with room to spare. Flight path visualizers show how straight routes become curves in reality. While technology improves accuracy, the fundamental challenge remains. No flat map perfectly represents our spherical world. The key is recognizing these distortions to make better informed decisions, whether planning a farm, sending aid, or understanding global relationships. The maps we choose inevitably shape the reality they represent. Every map you've ever seen is wrong in some way. Flat projections must distort the spherical Earth, stretching, shrinking, or warping reality to show certain features clearly. The Mercator map makes navigation simple, but blows up polar regions. Equal-area maps show true sizes, but twist familiar shapes. Peel back your map like an onion skin. What lies beneath the familiar shapes? That straight-line flight actually curves across the globe. Alaska only dwarfs Mexico on paper. Cartographers choose which truths to keep and which to bend. Next time you unfold a map, ask, what story is this projection telling? The real world hides between the lines.